Next, we have a growth and decay problem. So we know that our formula for growth and decay in differential equations is dx over dt is equal to kx. And the reason for this is that the growth and decay, remember where k is the constant of growth. Growth and decay, so x over t, so whatever x is the growth of x over t, it's proportional to the amount of the present x variable. So whatever we have here, this is proportional to this. So if this is getting bigger, obviously this is growing too, right? And if this is getting, if this is going down, then this is going down. So whatever we have at present, it's proportional to it, dx over dt. So let's take an example here. So K-Town had 25,000 people in 1970, and then it had 30,000 people in 1980. So if the population grows exponentially, find the population in 2010. So then we write our dx over dt equals kx equals equals k times x. We write it here, but instead we change it to dp because our x now is our population. That's the variable we're trying to figure out with respect to time. So dp over dt is equal to kp. Now, standard logarithms like I've shown on this, standard integrals like I've shown on this channel before, it's very similar. So you divide the p, you get the p's on one side, and this is a separable differential equation. So we could separate these, get the p to the left side, t to the right side, dt to the right side, and then we get 1 over p because remember we divided 1 over p. We moved it to the left side, so we have 1 over p on the left side and then dp, and that's equal to k dt multiplied to the right side. So we take the integral of this, and we get 1 over p times dp, the integral of 1 over p dp is equal to the integral of k dt. And since taking the natural log of p would give us 1 over p, taking the integral of 1 over p would give us the natural log of p, the absolute value of p, is equal to, and remember this is a constant, so we just add a variable to it if we're taking an integration, plus c1. So now p is equal to e. So what I did here was, if you have a logarithm, to cancel out the logarithm because we want p by itself, we're solving for p. To get the logarithm by itself, we simply just add an exponential to the other side and raise it all to an exponential, because remember, again, logarithms or natural logs and exponentials are related. They cancel each other out in many ways, and so that's how it works. So to get rid of a natural log, you just put the right side to an exponential. Now, we know that if we were to multiply these variables that have exponents, we would get one variable with added exponents. So we just work backwards and separate the exponents by separating the variables. So if we have e to the kt is equal to e to the c1. Now this is completely a constant. C is going to be a constant. Remember, e is just a number. This is a constant. So we get p is equal to plus minus e to the c1. And we know that e to the c1 is equal to c. We could just set this whole thing equal to c, just one constant. That's it. It's easy, right? And we do the plus and minus to remove the absolute value. So we got p by itself. It's great. Plus minus e to the c1 times e to the kt. And we're left with our almost final equation. P is equal to c, which is this constant. This whole thing is a c. E to the kt times e to the kt. Now, we know that at time 0 is gonna be our population, our original population, right? So p sub o, it's gonna be, so at time 0, p sub t, we're gonna get our original population, right? This is our initial population. Whatever time 0 is, whatever the population is at time 0, that's just what it's gonna be. So we could just write it as p of 0 is equal to initial population, right? At time 0, we get initial population. So p of 0 is equal to c. So what we do is we take the time. We're gonna figure out what c is. So we just sub in a 0, right? And we set it equal to c. And e to the k times t. We set it equal to this entire equation, and we sub in 0 for t, for time t. And now we get this entire thing just turns into 1, c times 1, because remember 0 times k is 0, e to the 0 is just 1. C times 1 is c. So we get p sub 0 is equal to, or p of 0 is equal to c, which is equal to the initial population. So C is equal to the initial population because we set P of 0 equals, we set it equal to the initial population here. So now we could now that we know C, we could rewrite this entire equation and instead write P, the initial population here. Our constant is the initial population. So P is equal to the initial population times E to the KT. Now, let's look at what the question says. In 1970, it had 25,000 people. And then it had 30,000 people in 1980. So that's a time difference of 10 years, right? Now let's apply that to our equation. So 1970 minus, not minus, to 1980 is equal, it's 10 years. So we could set our current population equal to 30,000. Now we can set, so it's just this formula. That's all we're doing here. Our P is 30,000 because it's 1980 right here. Remember, 30,000. Our current population. Our initial population was 25,000, and then E to the K, and we don't know what K is yet. That's what we're trying to figure out right now. Times 10 years. Our time is 10 years. So what is K? That's your constant. It's going to help us figure out the next part. So we divide, simple algebra, 30,000 divided by 25,000 we get is equal to E to the K 10, right? So 30,000 divided by 25,000 is 1/1.2, which is equal to E to the K times 10. Now, to remove the E again, like I said, logarithms have they're related with exponentials, so you just take the log of the left side. The logarithm of 1.2 is equal to K of 10, or K times 10, sorry. That's what we're left with. So now this is very easy. We just divide K by 10, or the right side by 10, and so we divide K times 10 by 10. And on the left side, we get log, or natural log of 1.2 divided by 10 is equal to K. And that's about 0.01823. Now that's your constant right here. That's your constant of growth, of however K works in differential equations regarding growth and decay. That's our K. Now part 2 was, if the population grows exponentially, find the population 2010. Very easy. In 1970, it's 2000 to 2010 is 40 years. So we do P is equal to population initial, E to the KT, and then P is equal to 25,000 for initial population, E to our constant of K, times 40 years, and then we get 51,840 people living in 2010. So yeah, that's how we do it.